I'm going to talk about a little case study on the Tulare Lake Basin and some thoughts on groundwater management for, especially for agriculture in California. So this map shows, for those of you not familiar with the state, it's a very descriptive of the water resources supply and demand in California. So we have this asynchrony in space and time in water resources in supply and demand. So we have most of our supply during the winter in the north areas of the country that are here in blue. This is where we have most of the precipitation. This is areas with lower precipitation. And we have most of the demand during the summer in the coastal areas that are highly populated, and in agriculture in the Central Valley, which is here, which happen to follow the opposite rainfall pattern. So for that, we have built one of the most engineered systems in the world that is able to move water all the way from the north, from the Shasta Dam, the largest surface storage reservoir in the States, even to places in San Diego, where we can even export some water to Tijuana. So droughts in California are a recurrent phenomenon, and this chart here shows some of the normal years and dry years, and we can see that they take all sorts of lengths and in time, and we have single-year droughts, multi-year droughts, and there's some. And over the geological time scale, we have evidence from tree rings that we have also droughts that have lasted for hundreds of years, or for a couple hundred years. California agriculture, which, as many of you know, is a powerhouse, is an industry of more than $54 billion a year in revenues, not even counting the processing industry that uses some of the inputs from agriculture, has more than 300 commodities. So we are not in a place in which we raise 2 or 3 crops a year. We have 300. That has some complexities associated with it. And we have 9 million acres, 7 million in the Central Valley, this area right here, largest in the U.S. in size, and the food basket for the U.S. For fruits and vegetables and nuts. And uses more than 26 million acre-foot of water a year. That is about 30 cubic hectometers a year, I think, for those working in metric system. And we have this trend toward permanent crops that is shown here. Back in the 80s, we only have like 18% or something of the crops were permanent, and now we have about 30% of the permanent crops. This provides about 2/3 of the income in agriculture, more than that, or more than that. So there's this phenomenon of converting some of the ag land into permanent crops. This is a map, an animation that shows a time series from 1998 or 97 towards 2012, no, actually 2015, oh, sorry. That shows this change in annual and perennial crops, and we can see that this is moving towards the more permanent crops. So this relies a lot, agriculture in many urban areas rely a lot on urban water. You probably heard a lot of figures in this conference about how much is of our water supply comes from groundwater. So this is a map that shows groundwater use in a darker bar, and surface water use in a lighter bar, in a lighter blue bar. And here we have from all the groundwater use, how much is used in each of the 10 hydrologic regions of the state. You can see that the Central Valley, especially the Tulare Lake Basin, that area that looked real reddish because of the low precipitation, uses most of a lot of the relies a lot of groundwater. It's about 2 for 1, the relationship here. The coastal areas have high reliance on imports from surface water from other places in the state, and a little bit on groundwater. So this is, as a result, we have some declining, some ongoing depletion. So in many of the basins in the Central Valley. So this is the Sac Valley, this is the San Joaquin Valley, And this is the Tulare Lake Basin, again, an area that relies a lot on imports, very low precipitation, and that is heavily relies on groundwater. So this, I like a lot this chart that we prepare at the center, which shows the cumulative acres in the state. So we have about 9.3 million acres, and we order those in values, in agricultural value, and acres and employment too. So we can see from this graph that most of the crops and that are classified as vegetables or nuts or other fruits provide about 85% of the total revenues and employment in the agricultural sector in the state. So these are crops of pretty high economic importance. However, this is provoking some of the demand hardening as well, and having some, and we have to deal with some issues with groundwater, as many of you know from the talks of this conference. So this is what we found in our two recent drought studies at the center in collaboration with the Agricultural Issues Center of UC Davis and ERA Economics with Professor Richard Howitt. We've been partnering for the past 3 years, funded by the California Department of Food and Agriculture. And we found that for the last year, as Secretary Ross was saying in the opening plenary session yesterday, we lost about a third of the total water supply to agriculture, but we were able to replace most of this loss in surface water, which was huge, with additional groundwater pumping. So we only had 2.7 net loss of the water supply to agriculture. So even so we were able to replace that with 6 million acre-foot of water for a net loss of about 10% of the total supply. So that's kind of helpful, and that's probably what we should be doing during droughts, just replace replace some of the surface water with groundwater. But what we should be do also is to keep into account what is going in the checkbook. We are just taking a little bit of the water bucket, but we need to balance on the years that are better. So that's the overall approach. So this costs about $900 million revenue dollars in crop revenue losses, and about 550 million thousand acres of fallow land. So we also have some losses for livestock and dairies of about $350 million, and increased pumping costs as a result of this. We have to pump at a much higher rate, which it will also come at a cost. We also, when we add these three effects, we have about 1.8 billion in direct revenue losses and about 10,000 jobs lost from crops in agriculture, mostly grains, field crops, and others. And when we put in the multiplier effect, this turns into 2.7 billion and 25 billion. So if you look at the 30% loss, 10% loss in the net loss in water, 6% loss in acres, and only 3.3% loss with respect to the income, we can see that this is a resource that has to be protected to cope with future droughts. So therefore, we have to use it during drought, but at the same time in later years, just balance the checkbook on how much is going in and how much going out. So this is how much the groundwater has saved us during drought. This is the increased pumping. So the red areas here are surface water losses. Blue here are the groundwater replacement. So this is how much increase we have in groundwater losses. So here, this map shows how much was the cost of pumping additional from, and you can see that increases the most obviously in the areas that mostly rely on groundwater, on surface water imports that have very little precipitation, such as the Tulare Lake Basin. So that comes at no surprise. And I put there links to some of this study. Other areas that are losing in the state, and this comes from a study we did with the Public Policy Institute of California, is the small rural communities. That's something that has been touched in some detail in this conference. So we have some groundwater quality issues with nitrate, as we've seen in the conference, and also we have loss of agricultural wells. So thinking in those two effects, we had this motivation to, oh, that was my animation. So we had this motivation to conduct a little survey-based approach that Brad presented in some detail earlier this morning, and I will just present a little summary of that on the Tulare Lake Basin. So this, and this is the area near the city of Tulare. It's about 27 square kilometers area right here. And we employed well completion reports, and also we constructed hydrographs from levels to groundwater, a time series of that over a certain period of time, to investigate how much of these wells will go dry over time and what happens especially during drought. So we constructed hydrograph like this that shows, and here we conveniently put the years that are dry years, and this is the current drought. You can see this 6 million acre foot in the entire Central Valley somehow kick in here as well. This is a basin that is considered critically overdrafted under Bulletin 118, and so this is an interesting area to explore. So some of the preliminary results indicate that we, from intersecting these hydrographs with distribution of the screen depths, top of the screen, bottom of the screen, middle of the screen, and bottom of the screen, we obtain about a percentage of wells that can get dry over this drought, and we find that about 10 to 20 with the preliminary findings. We're still working on some of the logs and things. 10 to 20% agricultural wells could have been lost during these droughts, and about 20 to 30% of the domestic wells that are much less deeper and have therefore are more susceptible to go dry. This is confirmed by some of the records that from the Tulare County that for this area gives people report some of the wells that go dry, and we are again analyzing how much these estimates are close to this. So in terms of cost, we have an average increase in cost of about $0.50 an acre foot, and this during drought, this slope in the cost is much steeper. So we are talking about close to $2 per acre foot per year in the cost increase somehow here. And so we also use some of the NASA following estimates. And we have here that in the skirts of the city of Tulare, some of the idle land in 2011, that was a relatively wet year, and some of the idle land in 2015, which is much higher. So there was a 44% increase in the idle land. These are not areas that are all supplied with wells. They also have some imports and some other local diversions that can also explain some of these increased shortage. So some preliminary findings: overdraft increases these energy costs and also decreases efficiency in wells, and we'll also need to have some cost for we also have some cost for reestablishing those wells, either maintenance, getting it deeper, or replace them. So that's several tiers of cost. Year-to-year increase is relatively small, but the big cost comes if we lose a well, if that well goes dry. So 10 to 20% of the wells are lost are agricultural, 20 to 30% are domestic. And this is a useful way of obtaining some information for better manage water in a region. So this approach can be helpful and extrapolated. Now, I have 1 minute left. So just thinking this approach in which we have a basin that relies only on water imports, that doesn't have any precipitation. So if it get out of 5 years is dry, we can grow only about 20% of the area in permanent crops. But as we get drier years, our ability to grow permanent crops decreases. So if we use this portfolio approach in which we can mix permanent and annual crops at with some proper local arrangements, we can obtain a higher profit. And I'll be happy to go over detail with this. Some concluding remarks. Groundwater remains the main buffer during drought. Climate change will bring similar, more frequent droughts. Funding is needed for having this interaction, make these interactions happen, and creative tools such as portfolio approach, markets, and monitoring measurement will be all helpful. And with this, I would like to thank some of the sponsors, the CDFA, and also acknowledge my colleagues. If I have time for questions.
How about this? Sorry to keep you waiting. So I think you have a slide about the depth and the number of wells. What's the sort of increment? Like, it's going to be another dry year, groundwater levels are going to go farther. How many more wells do you anticipate going dry in the area? Have you done kind of a sort of a depth, sort of a number of wells at different depths so you can kind of understand the impact of different levels of overdraft?
Yeah, the good news is that I have the person who did actually the work, so it's right here. It's Brad and Rob. So Brad, I have some.
So what I showed in my presentation.
We have a mic coming.
Oh.
Thank you. So what I showed in my presentation earlier was that if you extended out the drought conditions, you'd get anywhere to 30+% of the wells that we had studied in the area continuing to go dry. I'm trying to think. We just referenced it based on different screen intervals because the depths are different in each well. So I think we saw anywhere up to around 70+% of wells that if the drought were to become worse in the next 5 years and continue on, that could go dry potentially, just of the ones we'd studied. And we just also noticed from the County of Tulare data, just to add on to what Josue said, that they were all the way up to around 1,500 reported well failures as of recent. And it's hard to know what they mean by failures, but that's something to note.
I'm on the board of directors of a Bay Area water district. We've been doing water banking for a dozen years in Kern County. What is the best source of replenishing the Tulare Lake groundwater system?
Well, I don't have any thoughts on that other than trying to recapture some of the exceeding streams, some of the agricultural drainage, provided that is not affecting the quality of the underground. There's quite a few ideas there, but being mindful about salinization and nitrate issues.
Can probably help answer that too. And I don't need the mic. Just the extent of trying to capture more flood flows in the Tulare Lake Basin. There's been some talk about trying to use the old Tulare Lake bed to try and capture some flows that come down the Kings, Kauai, Tule, and Kern. Something like that could possibly help out with those deals. Looking at alternative sources, I know there are some that use oil field produced water down in that area. There's a chance to perhaps extend and try and use more of that as a portfolio in northern Kern County. But I think those are different options that they can use to even do a type of in-lieu system with groundwater banking partners up north.
Let's thank Josue again.